In my previous video about the power reporting deviation metric in hardware info, I suggested a simple way to counteract this inaccuracy, and concluded by asking, is there a significant difference in CPU performance between before and after the fix? Today I'm gonna answer this query, thanks to an inferential statistical analysis named Dependency test, executed via a program called RStudio. But why am I doing this? After all, it can be seen by eye that the performance after the fix is worse than before. Sure, there's a difference. However, without conducting the appropriate statistical test, I cannot say that this difference is statistically significant. This is the way. Before proceeding with the actual t-test, I must check that its three assumptions are not violated. Assumption number 1. The two samples are paired. True, since the same CPU has been tested in Cinebench R20 under two different conditions. Automatic PPT at 112 watts and corrected PPT at 88 watts. Assumption number 2. There are no extreme outliers in the differences between the two paired samples. True, since two-case Fancy's method detects 238 as an outlier, but not an extreme one. Assumption number 3. As the sample size is less than 30, the distribution of the differences must follow a normal distribution. The Shapiro-Wilk test is designed for verifying whether this assumption is met. If p-value is greater than 0.05, the distribution doesn't deviate from normality, so the null hypothesis is true. If p-value is less than or equal to 0.05, it does deviate, so the alternative hypothesis is true. In this specific case, the p-value is 0.282, therefore H0 is accepted. A small excursus. If the assumption of normality was violated, I couldn't use the parametric t-test, but a non-parametric one, the Wilcoxon signed rank test. Now the descriptive statistics of the two samples are here. Mean, variance, standard deviation and standard error. Through this latter and the confidence coefficient associated with a level of 99%, I can compute the margin of error, and as a consequence the confidence interval. I will not go into details about the role of these statistics, because it's unnecessary for the purpose of my video, but it's still important to point them out. Finally, the paired t-test. As I said earlier, it's designed to compare the means of two related samples. If p-value is greater than 0.01, the mean of sample 1 is not significantly different from the mean of sample 2, so the null hypothesis is true. If p-value is less than or equal to 0.01, the mean of sample 1 is significantly different from the mean of sample 2. So the alternative hypothesis is true. Since RStudio returns a p-value of 7.24 to the minus 10th and a Cohen's d effect size of 8.413, H0 is rejected and H1 is accepted. The difference between these two means is statistically significant and its magnitude is huge. In simpler terms, the R20 average score with PPT Auto is significantly higher than the average score with PPT 69. Basically, my PPT correction drastically reduces the CPU performance in Cinebench R20. Now I know the real impact of my choice. If I let the motherboard lie, I'll gain a substantial amount of performance at the cost of 10 degrees Celsius more. If I don't let it lie, I'll lose a substantial amount of performance for the benefit of 10 degrees Celsius less. The decision is mine. Farewell for now.